Na festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou, passo bem sou. Na festa do fim de semana. Festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou. Na festa do fim de semana, semana, pana, 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 pana. Na festa do fim de semana. Pana, 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 de semana. Pana, 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 de semana. Pana, 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 de semana.
Hello everyone and welcome to my new stream. Today we are gonna continue learning OpenGL. Now let's do a quick recap of what we did so far. So okay, we are starting to get into this system. Hold on, let me drink water because I'm really thirsty. So now we know what glue and GLFWU are, right? Glue is the binding library and GLFWU3 is the library that provides some window handling and event handling systems, things like that. So let's do a quick recap for what we did so far. Let me check if I'm streaming. Yeah, you're streaming. So first we define a window, a GLFW window. Then we initialize it. If it doesn't, we exit the program. The process will return -1. Then we assign the window with a create window. We use the method from GLFWView, and this is the size, this is the title, this and these two are probably the flags. Then we checked if the window is properly initialized. If it's not, we terminate GLFWView and exit with the status -1. Then we create a context and we pass a window. I'm still not sure. This is the third time. I'm still not sure what a context is, but anyway, we use glue in it and it's check if this is initialized properly. If not, we will print an error and then exit with the status -1. Then we get the string of the GL version and print that out and then put a new line here. Then we have an array of positions, right? So right now we have, this is the buffer, like this is a vertex buffer, and this is and we store this inside, like we told OpenGL that this is a buffer, and we generated a buffer. The quantity is specified right here. So we generated a buffer and it's stored inside this. And the ID of this of the buffer of the new buffer is stored inside this variable. Then we bind it because OpenGL is a stateful architecture. Follow this. It has this status architecture, and we have to assign the state to this buffer, like GL array buffer. Then we have the buffer. Then we have GL buffer data, and this is where basically we allocate memory. I'm not sure, but we can check. We can check docs.gl. So let's check real quickly. So we have, where is it? Here it is. Let's check GL buffer data. So we have this GL buffer data or named buffer data. Oh, you can also have a name. This is the buffer. I'm not sure how this works, but it's kind of, I don't know. Create and initialize a buffer objects data store. So so this is where the object is initialized. So it's like it's like allocations, right? So we have GL array buffer for vertex attributes. We have this thing here. I don't know what that is. Atomic counter storage. So it's like a single atomic number that I don't know. GI copy read buffer, write, dispatch, draw, element array, pixel pack, query, shader storage, texture buffer. We have many things here. So let's read the description. GL buffer data and GL named buffer data create a new data storage for a buffer object. In case of GL buffer data, the buffer object currently bound to the target is used. Okay. So it's a stateful machine, right? For GL named buffer data, a buffer object associated with the ID specified by the color in buffer will be used instead. Okay, this is the stateful method, and this is the stateless method. Like you pass one more argument, which is the ID, right? So, but the thing is, there are 4 arguments here, but there is still 4 arguments here. Like, what's actually the usage, right? What is this? I don't know. While creating a new storage, any pre-existing data will be deleted. The new storage. Yeah, it's like the allocation, right? This is where we allocate data. So we have streamed, okay. So this is like the method we use. Like, yeah, this is the frequency we use to have this part, and this is static. Okay, we use the static. The data store contents will be modified once and used many times. I will probably use dynamic, like, for changing things. I don't really know, honestly. We should use the vertices to draw. The data store contents are modified by the application, and use it as the source for GL drawing and image specification comments. The data store contents are modified by reading the data from the GL and used to return that data when queried by the application. Hmm. I'm not sure what's the actual, I'm not sure what's the actual difference. Uh, I don't know, but yeah, we should use we used we followed this playlist, and the journal used static and draw in this case, right? He explicitly said multiple times that he's doing for learning purposes. So it's not actually, maybe the settings might not be the best for game engines or things like that. And then let's reopen this. Then we enable this attribute, right? GL enable vertex attribute array, and I think this is the pointer. Hold on, let me just GL enable vertex attribute array, and then we'll pass the index. Probably. Let's check the documentation. GL enable vertex attribute array. What is the index? Enable the generic vertex attribute array specified by index. What is the index? Like, I put 0 here, but I'm not sure what the index actually is. I don't know. Then we have GR vertex attribute pointer. Then we have, this is 0 because this is the index, because since we are using vertex positions. No, wait, what the fuck? Wait, no. This is the position, right? This is the position attribute, not the vertex attribute. I got confused. The position attribute inside the vertex, because this is part of the vertex. So we enable the position attributes, and then we enable, and then we assign. Wait. We point this, we map this using this function, and we have the index, which 0 means positions, 2 because we are using two-dimensional values. We have the x and y values for the positions, and GL float because it's a float. This is false because this should be this. The floats are already normalized. No need to normalize those values. Then we have the size in megabytes for each position attributes, and then we have this pointer. So this is the first the pointer of these values. This is 0 because it's on the very beginning of the array. Then we created a vertex shader. I'm not sure what that is. Like, there is this layout location equals 0 in vec4 position. I guess I need to learn a new language, the GLSL. Yeah, this one. Then we have void main. Then we have then we assign the position retrieved by this location here because we are pointing on 0, and then we have the same thing but with the color, and then we draw I don't know why we do this, but we need to set the color to these values. I'm still confused. I'm still confused with this part of the code, but we did nothing here. Like we just created an example to display triangle. So we created a shader. So what to create a shader, we created a function here. We have vertex shader and fragment shader. So vertex shader is like they are both strings that contains code to be compiled. Then we go here, and in create shader we create a program, because when you use graphics you have to create a program, and this program contains multiple shaders, since shaders are just programs run in your GPU, right? So we have VSFS, which stands for vertex shader, and fragment shader, which we use here to compile this shader. So we when we create a program, we have to create the shader. Like we create a program, we create the shaders, we check if there is no error. We also need to compile it, by the way. So we give the source and compile it, and then we attach these two and link them together, and then validate it. And if there is no error, we will skip this part. If there is, we will go here, and then we delete the existing shaders, because the program is already compiled, so we don't need them anymore. And then we will return the ID, right? The ID of the program. So we will use this program, and this we will pass the ID of the program. Also, the fuck is going on? Why is search taking so, why is search using so much GPU? I don't know. Then we will loop, and this is like the job pipeline. We can, I guess, like the things gets cleared, then we draw erase. So we have the triangle, and what the fuck is this? Oh, what is this? So we have the triangles, but then we have 0, 3. 0 is the 3 are the wait. Let me just. So let's go here and then gr draw erase. This is the first, and this is the count. Okay, this is the first index, I guess, and this is and this is how many vertices there are. Okay. Jesus. So we have the mode, job points, line strip, line loop, lines, line strip, agency, lines, adjacency, triangle strip, triangle fan, triangles, triangle strip, adjacency, triangles, adjacency, GL patches. I don't know any of this. This is the first index. and this is the count. Okay, it's actually pretty self-explanatory, the rest. Then we have GLFW's buffers. I'm not sure what it is. This is probably to handle events, something like this. And then when we exit the loop, we will delete the program, terminate GLFW, and return 0. That is what we did so far, right? So now let's keep watching the series, this playlist. Let's keep going on because we want to create big things, right? How I deal with shaders with OpenGL, index buffers, dealing with errors, uniforms, vertex array, abstracting. Okay. Oh Jesus, there are many things to cover. And let's see what we get. So let's move on this video.
So you want to start a coding?
Get the fuck out.
My name is the Cherno and welcome back to my OpenGL series. Mixing it up a little bit with the set. I mean, last one, you guys were certainly noticing that I waved my hands around a lot. I was coming pretty close to hitting that cactus occasionally, and that was just, I don't want to lose a hand. So we're basically mixing it up, we're basically changing. I thought I'd make a subtle kind of change just to get rid of that whole risk of losing a hand. I didn't want to overreact or anything like that. So I changed the set slightly, kind of got rid of the cactus.
Wait.
That whole risk of losing a hand. I didn't want to overreact or anything like that. So I changed the set slightly, mixing it up a little bit with the set. I mean, last one, you guys were certainly noticing that I waved my hands around a lot. I was coming pretty close to hitting that cactus occasionally, and that was just, I don't want to lose a hand. So we're basically mixing it up, we're basically changing. I thought I'd make a subtle kind of change just to get rid of that whole risk of losing a hand. I didn't want to overreact or anything like that. So I changed the set slightly, kind of got rid of the cactus. It's still in this room, but it's all the way over there. Anyway, hope you guys like this new kind of format. It's going to be a lot more casual because I'm not a big fan of being professional, to be quite frank with you guys, and hopefully this is just going to be a little bit easier for you guys to watch and listen to as well, without kind of me going through everything like a robot and just quickly kind of having to spend like an hour or two editing every single video. So anyway, welcome back to my OpenGL series. Last time we talked about shader stuff, and in fact the last 2 episodes we've been kind of talking about shader stuff. Specifically, we talked about what shaders were, and we actually had to go at writing a very simple vertex and fragment shader that basically just made our triangle red. If you guys haven't seen that episode yet, definitely click up there because you need to watch that in order to get this video. Because what this video is going to be about is just basically continuing on with that, and more specifically, I'm going to show you how I like to deal with shaders. Because kind of what we've been doing right now with the code is basically, I mean, if we look at the code that we had last time, we have this function where we compile a shader, and then we kind of create it and all of that, but we still have to basically take it in. Well, the biggest problem here right now for us is that we still need to take it in kind of as strings. And that's a bit of an issue because, well, first of all, looking at these strings, you can see we have to add new line characters and quotes everywhere. It's just not very like comfortable for us to write shaders at this point, and it's pretty easy to just miss a new line or something like that and end up with some kind of bug, and I don't want to really do that. So we're definitely going to fix that up so that we can actually take our shaders in from a file. And specifically, what I see a lot of people doing, which is, I mean, completely reasonable because OpenGL does kind of enforce it to a degree, is that what people will actually do is create two different files. One for the vertex shader and one for the fragment shader. I'm really not a fan of that, to be honest. I mean, having two different files, like, why? I mean, in some cases, it can be useful to divide shaders up. For example, you might have a vertex shader which just takes in like a certain amount of parameters, certain amount of inputs, and just outputs a position, and that's it, or provides some kind of data to the fragment shader. And it might be a really simple vertex shader which you can pair up with 3 different fragment shaders, for example. And in that case, you might argue, well, okay, you know, I'm loading this file, I don't want to necessarily tie the two shaders together, like the vertex and the fragment shader together. I don't necessarily want to do that. That's one argument, but we've got to, like, we'll deal with that as well in a minute here. But the big thing is that I don't like having to, like, why have 2 different files, right? There's no actual reason for that. It's actually a little bit annoying. You have to make 2 different files. You have to read in 2 different files. When you're editing them, you have to, like, switch between the two or have them open side by side. It's just not very comfortable. And I'm all about comfort. Like, clearly, I'm sitting on a couch here instead of a chair and a table. So what I like to do
I'm
is
sitting
combine the two
on a
shaders into
wooden
one
block
file,
and it's
right? Just
so
have one
uncomfortable.
file
You
with a
have no
vertex
idea.
and a fragment shader. And of course, in the future, if you want to use one vertex shader with a bunch of fragment shaders, you can still do that. You can still, because obviously when we give the shaders to OpenGL at the end, they still need to have that clear division, right? We can't just simply give OpenGL one string of source code and then it can deal with it. It still needs to kind of know, it still needs to kind of have that distinction between this is my vertex shader source code and this is my fragment shader source code, and we're still going to provide it with that. It's just on our side, basically, as the user, as the programmer, as the developer writing this kind of code, we're going to write it all in one file, and I'll show you how we divide it into 2 shaders in a minute. This is very much like DirectX. You might actually kind of, throughout the series, you'll probably see me reference Direct3D 11 specifically quite a lot with how I actually organize my OpenGL code, because when you deal with game engines, you'll be using multiple APIs, multiple graphics APIs most likely, if it's a serious engine. And you kind of will probably, if your engine supports Direct3D, or even if it doesn't, you'll probably find yourself making OpenGL behave more like DirectX, because DirectX is just a better API. Anyway, let's get into some code and I'll show you how all this is going to work. So the first thing we're actually going to do is just create a file which contains these 2 shaders so that we know how we're actually going to deal with them. So over here in my kind of source directory, I'm actually going to right click on OpenGL, hit add, and then new folder. We're going to call this res, which stands for resources. And then under that res folder, I'm actually going to create another folder called shaders. And this is specifically going to be for shaders. We will have other resources like textures and stuff like that in the future.
Okay, let's do that. So we create a new folder. We call it res, and then we will create another folder, shaders. Okay.
Future. So I just want to keep all of this really nice and tidy. We'll right click on shaders, hit add new item, and then here I'm just going to add a file. Now, it doesn't matter what you click here because we're kind of going to change the extension anyway. We're just going to call this shader.shader, or specifically we might rename this to something like, well, I don't know, it just makes our triangle red. We're just going to call it basic.shader because this is just going to be like our basic shader that we deal with. I'm going to hit add, and now we have a shader. You can see that it's not showing up as like the C++ icon, which is very important. We don't want to accidentally compile this as C++ code.
Okay, let's do this. So let's add a new element, and then we had basic.shader, like that. Oh wow, this isn't, wow.
Because of course it won't compile. Let's go back to application.cpp. I'm going to copy this entire kind of block of code, and I'm going to paste it into this file. Now we need to clean this up a little bit. Specifically, I'm going to get rid of the string, of course, from both.
Yeah, let's do this. Let's go here and then let's paste this right here. And yeah, we have to, oh god, we have to get rid of all of this stuff right here. Just like that, right? Probably. Oh god. Okay, it should be okay now, right?
These here, and then to actually clean this up, we could go through this kind of line by line. It's going to be a bit hard, so I'll show you guys a bit of a trick. If you hit Control H, that will bring up the Find and Replace dialog, which you can see over here. We're going to grab quotes and replace them with nothing. If you hit Alt A, or I think there's a Replace All button here, Alt A will get rid of all that, and then finally we want to get rid of the new lines as well. So I'll also replace \n with nothing. Alt A, done, and there we go. You can see how much easier that was than kind of just going through this code and cleaning everything up manually. Okay, fantastic. We've got this. Kind of hard to tell the distinction though between a vertex and a fragment shader. So what I like to do is just come up here to the top, and I'm going to hit hash shader and then vertex. Okay, and then I'm going to copy that, and just above the fragment shader, call this fragment. So when we have all of our different shaders, we might have other shader types like tessellation shaders or something like that, geometry shaders, that kind of stuff. We can also probably add a section for that. But for now, you can see that I've clearly kind of divided this into my fragment shader and my vertex shader. Don't worry too much about the syntax highlighting here, because we have actually specified the .shader extension. Visual Studio is probably going to try and highlight this as if it was HLSL, so like a DirectX kind of shader. But anyway, that's still kind of sort of helpful for us because it highlights some things like numbers, and kind of makes that easier to see. But you can see this is kind of my strategy for laying out shaders. It's very easy. You can see what's going on all at once. You don't need to flip between two different files. And it's just, yeah, it's just really nice and easy and clean and organized. So let's go back to our application. I'm going to get rid of this entire block here now. Now, to kind of understand what's going on here, we have our create shader function, which takes in the 2 strings of source code. We still need to provide it with 2 different strings of source code. So now, really, our plan is just to take this file and divide it up into 2 blocks of strings, right? Into 2 strings. Our fragment shader source code and our vertex shader source code. Let's go back to application and do that. I'm going to scroll up here to the very top. We'll just write this function at the top, why not? Static, we'll make it void for now. And we'll call this parse shader. And then I'm going
Fai clic per scoprire le
Shut up.
going
Okay.
to just make this take in a const std string, and this will be our file. Might call this file path. And the way that we're actually going to read this in is, of course, first of all, we need to open a file. And I'm going to do this in a bit of like a C++, modern C++ way, not necessarily the way that I would find. Might call this file path. And the way that we're actually going to read this in is, of course, first of all, we need to open a file. And I'm going to do this in a bit of like a C++, modern C++ way, not necessarily the way that I would personally read files in a game engine, because C++ tends to be a little bit slower than the C kind of file API, but because this series is obviously just about OpenGL, I want to kind of write code that's a lot easier to read and a lot safer and all of that. So I'm just going to basically include something called fstream, which stands for file stream. And then over here, I'm going to write std ifstream. We'll just call it stream. This stands for input file stream. And then I'll kind of give it that file path. That's the actual file that we're trying to open here. That already opens the file. So now what we need to do is actually go through that file line to open here. That already opens the file. So now what we need to do is actually go through that file line by line and just check to see, hey, are we specifying a certain shader type? Because we've kind of added our own syntax, right? We've got this hash shader vertex thing here, which basically says, hey, this is a new shader section, and this is the type of the shader that it is text thing.
Wait, hold on.
By line already opens the file.
Oh my god. Yeah. So we have stream dot close. I don't know why it errored before. I don't know why, but okay.
So now what we need to do is actually go through that file line by line and just check to see, hey, are we specifying a certain shader type? Because we've kind of added our own syntax, right? We've got this hash shader vertex thing here, which basically says, hey, this is a new shader section and this is the type of the shader that it is. So we need to kind of read in that. And we're going to go through the file line by line. And the way we'll do that is we'll actually do while stream we'll use a function called getLine. So while getLine stream, and then we'll make a string here called line, which will contain our actual line. While that doesn't equal 0, basically. Now getLine is a function that actually is inside the string header, so we need to include string. So while getLine is still kind of valid, which means there are still more lines header, so we need to include string. So while getLine is still kind of valid, which means there are still more lines for us to read inside the file, we're going to just basically check to see line.find if that...
I don't know if you remember that the last time I explained why I should include string. That's why. Yep.
Actual line contains our shader kind of custom syntax token here. And if that doesn't equal std string npos, which is basically an invalid string position, because find will return us the actual string position. You can see it returns a size t. It doesn't return a boolean or anything like that with whether or not it actually found our string. It actually just returns us the position of it. So if it's npos, it means it hasn't found it. So if it has found shader on that line, we need to basically find which type of shader it is. And again, I'm just going to use line.find if it's going to be vertex. If it finds vertex, then we're going to basically have to set the kind of mode to vertex, which we'll do in a minute. And otherwise, though, if it finds fragment, so if that...
I don't know if I should do that. Like, I think if we can just, yeah, I'm just gonna follow this video.
Doesn't equal std string npos, then we're going to set the mode to fragment. Okay, so that's kind of how this is going to work. We're just going to go through it line by line, and we're going to keep adding vertex. Well, if the type is set to vertex, we're going to keep adding these lines basically to our vertex shader string. If it's fragment, we're going to add them to the fragment shader string. Pretty simple. So now we actually need to add the strings that we're reading, add these lines that we're reading into some kind of buffer where we can just pile on line by line what the vertex shader and the fragment shader is. So to do that, I'm going to use something called string stream. So we'll have to include that, and that'll be under include stream. If we scroll down here, I'm just going to make two different string streams. So we'll call this SS, and I'm actually just going to use a kind of stack allocated array here to have...
Bro. Alright. Okay, so no, I'm still streaming. I think I'm lagging. That's not good. Let me just... Okay, I am.
Have two of them.
So, okay, let's create a string stream. Let's do this wait, string stream ss stream or ss, right? Shut up.
One of them's going to...
I accidentally mute myself. Oh my god, don't do this.
be for the vertex shader, of course. One of them's going to be for the fragment shader. And the idea is we need to have some kind of mode as well. So are we currently reading in a vertex shader or a fragment shader? to do that, I'm just going to create an enum class here called shader type, and then we're going to have none, which is -1. Then we're going to have a vertex, of course, which is 0, and fragment, which is.
Okay, let me just create this animation shader type. So no one is 0. I mean -1. Then we have vertex 0 and then fragment 1, right?
I'm being very explicit with these numbers, and I'll tell you why in a minute. We're also going to store the current shader type that we're reading in, so we'll set this equal to none by default. Okay, cool. So if we find vertex, if we find shader vertex on a line, we need to set the mode or the type to actually be shader type vertex, and then
Oh right, yeah, this isn't C. I have to retype this. Just like that.
Of course, for fragment, we can set it equal to fragment. I'm kind of setting this up loosely. I could be a little bit cleaner with my code and actually have some more functions and stuff like that to work out what the type is from a string, but again, it's just overkill. This is a really simple function. So
we assign the type right here, right? Then we have vertex, and then we have fragments.
Once I've done that, if we see hash shader on a line, we know that we need to set a type. Otherwise, if it's any other kind of line of code, then we actually need to add it to either the vertex or the fragment shader source code. And the way we do that is to this string stream. Let me just get rid of this extra space. To this string stream, I'm going to basically push the line into it. Now I need to know which one to push to.
What the? Oh, right. Forgot to add this.
And that's why we've got the shader type. So I'm going to grab the type and just cast it to an int and use it as an index into this array. We know that the array contains 2 elements, and we know that basically the first element in that array is going to be vertex, and the second one is going to be fragment. So I'm kind of using arrays here in a little bit of a clever way. Vertex, and the second one is going to be fragment. So I'm kind of using arrays here in a little bit of a clever way to actually automate this a little bit more, so that I don't have to have a branch where I basically say if the type is vertex, add it to the vertex string stream. If the type is fragment, add it to the fragment string stream. I can kind of just use the type as an index into the array, which is just going to be a little bit better basically. So over here, I'm going to basically add line into that string stream followed by a new line character, just like that. And that's pretty much it. I mean, if you look at this code, this should divide our shader into 2 different types and add them to the appropriate string stream. So finally, at the end here, I need to actually return my code. Now we have a little bit of an issue because we are trying to return 2 strings, and of course, you can only return you can return one variable in C++. So how do we return 2 variables? Now we could use something called a tuple or a pair. I actually have a lot of feelings about that. Actually, I might make a C++ video this week maybe that actually deals with this kind of multiple return type thing specifically. I think I will actually, that's probably a good idea. I don't like using that stuff, and I'll explain why in the C++ video. I don't want to bore you guys here, but what I would do if I need to kind of return multiple types here is I would actually make a struct called shader, I don't know, shader sources or something like that. We might actually just call this shader program source, and this is actually going to contain our, we'll call this vertex source. I kind of like to capitalize it. I'm kind of treating this almost like a C# property. That's why I'm capitalizing this, because they are just public fields. So we'll take in vertex source and fragment source. Okay, cool. Very basic struct, and I'm actually going to just return that struct. And then at the end here of my very basic struct, and I'm actually going to just return that struct. And then at the end here of my function, once I have the 2, once I've built up and I've read all of the source code from that file, I'm just going to return basically a struct, this struct, right? So I'm going to set the vertex source to be ss0.str and then ss1.str, okay, which gives us the string back from the string stream. And that's all we need to do right now. So this code should set us up with the actual shader source code for both the vertex and the fragment shader. Awesome. So now let's scroll down and actually test the stream, and that's all we need to do right now. My source
So-
should be SS. Since I've built up and I've capitalizing this because they are just public fields.
This will return
So
shader
we'll take a
plus
vertex
source,
source
right?
and fragment source. Okay, cool. Very basic struct, and I'm actually going to just return that struct. And then at the end here of my function, once I have the two, once I've built up and I've read all of the source code from that file, I'm just going to return basically a struct, this struct, right? So I'm going to set the vertex source to be ss0.str and then ss1.str, okay, which gives us the string dot. And I've read
Wait, hold on. What
this
did you
because they are
put
just
here?
end here of cool, very basic struct, and I'm going to once I've built up a struct str stream, and that's all we need to do right now.
Right, I forgot to put this.
So this code should set us up with the actual shader source code for both the vertex and the fragment shader. Awesome. So now let's scroll down and actually test this out. So the first thing I'll do is I'll kind of, we might just get rid of our shader for now, just by commenting it out. I just really want to see if my function works first, to be honest. So we'll go shader program source or something like that, equals path shader, and then we'll take in our file path, which is just going to be res/shaders/basic.shader, which is our file path, which is just going to be res/shaders/basic.shader, which is our file path, which is just going to be
Wait. Parse shader, then we have res.shader slash basic dot shader, like that.
res/shaders/basic.shader, which is our file. So res/shaders/basic.shader. Now this is kind of the first instance of us actually reading a file in C++ in the series on my channel. So basically what you need to know about this is that if you specify a relative path like that, so not something that is an absolute path, you know, like C uses whatever, starting from the C drive or whatever, since we're specifying a relative paths are always from the working directory. Now, if you run the executable outside of Visual Studio, the default working directory is just going to be the directory that contains that executable. So everything will be relative to that. But if we're running this through the Visual Studio debugger, the working directory is actually set by our Visual Studio debugging kind of properties. So if we right-click on the OpenGL project, hit Properties, you can see over here we have a tab called Debugging, right? And under here we have a working directory. You can see here that it's set by default to our project directory. So we know that this file is relative to the project directory. That is the directory that actually contains our project file, which in this case is this directory, which just has our vcxproj. So you can see it should be relative to this. So res/shaders/basic.shader. And that's exactly what I've written over here. Now that we've got this, let's actually just see out source.vertex source, and also I'll do the same for fragment source. Now to divide this in some way, just to make it extra clear, I'm also going to copy this kind of twice here and write, you know, vertex like that and fragment, so that we can really see the two different shader types we have. And I'm just
So let's do this. So we have vertex, std, and then we copy this. Then we have source dot vertex source. Then we have fragment, and then we have source dot fragment source. Right? That's what we are going to do. Let's try to run this app and see if everything works. Yep, we have it working right here, and it runs perfectly fine, right? So that's what we are going to do. I mean, that's what we did, right? And everything works. I will comment this out. So
I'm just going to hit F5. Okay, I've got one more syntax error here when we do GL delete shader. By the way, this code was wrong from the last episode. I added a little thing, kind of just in Premiere Pro, like in my video editing software, I just add a little kind of note being like, this is what the function should be. It should not be GL delete shader. I don't know why I wrote that. It should be GL delete program, okay? Because shader is actually just one shader type. Our program is actually going to delete our program. So that's what it should be. Let's comment that out for now though, because we did kind of comment out that shader code. Let's hit F5 to run this program. Hopefully we can see our parsing working correctly. So if I go to my console, you should see that we have vertex and then the vertex shader and fragment and then the fragment shader. So it looks pretty good to me. They look like they're our correct shaders. Nothing crashed or anything like that. Looks pretty perfect to me. Let's go ahead and actually pipe that into our source code, or specifically into our shader compilation function. So I'll bring this back.
Oh, wait, whoa. So we have it right here. This is the vertex and this is the fragment. Yep. Whoops.
And I'll bring back my GL delete program as well. And then instead of kind of providing vertex shader and fragment shader, now that we've got this, we can just provide source.vertex source and source.fragment source, just like that. Let's hit F5. And you can see that we get a red triangle. If I go back to my basic.shader file, let's go ahead and change it. Let's make it, I don't know, let's just make it a nice little blue. So I'll make it 0.2, 0.3, 0.8, and then hit F5.
Here's how I balance.
As you can see, we get a nice blue triangle. Awesome. So I hope you guys enjoyed this video. We basically just took what we had with shaders, made it a little bit better, combined it all into one file, and now we can create shaders from files, which is pretty cool and going to be way more easier. It's going to be way easier for us to actually do that as we progress on with this series. Now in the future, we will probably abstract all this into a class as the code base kind of keeps growing. For now, we're not going to worry about it. We're just going to move on. We've covered vertex buffers and shaders. The next step that I really want to cover is going to be about index buffers, okay? Because we need a way to actually render our triangle using something called an index buffer, and we'll talk about why we want one of those, what that actually is, and all of that in the next video, because it's probably not that apparent. The need for it probably isn't that apparent with a triangle, but as we kind of get more complex with our geometry, I mean, even if we try and render a square, which is pretty complex, right? It's going to benefit us. It's going to basically be a huge benefit for us to use something called an index buffer. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. You can help support this series by going over to patreon.com/thecherno. There are some pretty cool rewards. I mean, I'm not going to lie. I would never lie to you guys, right?
So let's go here. So we have index buffers and then we have everything else. So this is the 9th video. Okay, that's cool. That's cool.
Hey, what's up guys, my name is Echano and welcome back to my OpenGL series. So today we're going to be talking all about index buffers. Last time we talked about shaders and also before that vertex buffers. Check out those videos if you haven't already. But today we're going to be focusing on something new, something called an index buffer. Now, before I kind of define what an index buffer actually is and we get into talking about why we want to use them and what they actually are, let's just think of a basic problem that we might have in graphics programming. We want to draw a square. Up until now, we've just been drawing a triangle. That's it, just one single triangle on the screen. Everything's been fine. It looks like the way that we're kind of doing that in our code is pretty efficient. However, let's try and draw a square. So what do we need to do to actually draw a square? Well, everything that our GPU actually does comes down to triangles. We might talk later about why that is, but for now, just picture a triangle as pretty much the smallest number of vertices we need to represent one flat kind of plane with a normal that is with a surface. Try and draw a square. So what do we need to do to actually draw a square? Well, everything that our GPU actually does comes down to triangles. We might talk later about why that is, but for now, just picture a triangle as pretty much the smallest number of vertices we need to represent one flat kind of plane with a normal that is with a surface normal that is pointing in a single direction. Because of that, GPUs tend to kind of use triangles as their rendering kind of primitive, right? So everything's based on triangles. So when we try and draw two squares, or rather, sorry, when we try and draw a square, it's really just a triangle, right? Or specifically two triangles. Anything we draw is made up of triangles. So a square is just two triangles, right? 1, 2, that's it, 2 triangles. So let's try and do that with our current setup and see what happens.
What is
So over
that?
here we have basically this set of vertices here. Let's just run this application and see what we've actually got. We've got this triangle here, a nice blue triangle. If we take a look at the code, we've got these 3 vertices. If we try and draw a square, well, let's think about that for a minute. I'm just going to open Illustrator here so I can draw you a diagram. Instead of us kind of drawing our triangle like this, which is what it is right now, we want to kind of draw a square out of 2 triangles. And the way we can do that is just by drawing 2 triangles like that, right? So we kind of have one triangle over here and one triangle over here. And drawing those 2 triangles separately, kind of like that and then like that, or however you want to do it. In fact, we're probably going to do it like this and then like that. So that's how we're going to actually make up that square. So let's talk about which positions these might actually be. So this one over here we know is kind of going to be negative 0.5 in both x and y. That's kind of what we've got over here, right? The next one, if we come over here and we kind of draw this in an anti-clockwise fashion, then we're going to be drawing this vertex first, then this vertex, right? So if we go back to our source code, that's basically going to be negative 0.5 in x and y. This one's going to be positive 0.5, and then still keeping negative 0.5 for y. And then we're going to lift y up to positive 0.5 and also keep x like that. So
Let's check if this is the case. So we have to draw some triangles, right? So let's put this 0.5 half, and then this is minus 0.5 half, and this is a positive value, and it should be like that.
So if we just run this program now, we should have that first triangle drawn. As you can see, that's what we get. Okay, so now we need to draw the second triangle. So let's start off with drawing this vertex here, then this vertex here, then this vertex here, to kind of keep going in a counterclockwise fashion. So back to our code, and we're going to add some vertices here. I'm just going to get rid of this 6 here so that we can have as many as we need. I'm going to copy and paste this vertex position because it's going to be exactly the same, of course. These 2 vertices are actually the same. And then I'm going to add one more vertex, for that'll be the top left corner, which is going to be negative 0.5x and positive 0.5y. And then finally, this vertex over here is also kind of the same as this vertex, 0.5y. And then finally...
Okay, let me just set this up. So we have this right here, then we have this, then we have this.
This vertex over here is also kind of the same as this vertex. So that'll be the same as the very, very first one here. So now we have 6 vertices. If I come down over here, we need to adjust the size of our vertex buffer so that it can actually take in all of this.
Yeah, let's try to do it. I'm gonna try to do it by myself. So set this to 12, and then that's pretty much it, I think.
Memory. So I'm going to, instead of just changing this to be 12, I want to make it 6 times 2 times size of float, because of course each vertex here is the size of 2 floats, and we have...
Yeah, we can do this. So we have this
6 vertices. It's just a little bit easier to read. If I scroll down here, the other thing I need to change is instead of just drawing 3, we of course need to draw 6. So in my GL draw array, I'm going to change this to 6 and then hit F5. Alright, there we go, pretty cool. So we've got an actual square now. Or specifically, this is a little bit rectangular because our window is actually not square. So that seems pretty good. I mean, we managed to draw a square. It wasn't too difficult, but there is something a little bit suboptimal about the way that we're actually drawing this square. And specifically, let's take a look at our vertices. So back over here in our actual vertex kind of array that we have here, you can see that what we're actually doing is we're repeating ourselves. We've got this vertex over here twice, right? And we've got this one, this first and last one, is also exactly the same. These aren't completely unique, which means what we're actually doing is we're kind of duplicating our memory. We're storing these same bytes of the same vertex positions in our GPU memory multiple times. And that's a little bit wasteful because, well, GPU memory isn't just infinite, and we do want to keep that down. So what we can actually do is use something called an index buffer, which allows us to reuse existing vertices. Because if you think about it, what we really want to say is draw kind of these 3 vertices like this, and then maybe draw these 3 vertices to make up the second triangle. This is much easier. This is going to be much easier if I just show you on a diagram. I don't know why I'm doing this. So let's go back to Illustrator. It would be fantastic if we could just say, and let me just change my color over here to maybe red, if we could just say, I want to draw this vertex, then I want to draw this vertex, then I want to draw this vertex, and then I want to draw this vertex again, this new vertex over here, and then this first vertex again, right? Because that would be all we would need to really say to draw this part, and then just draw that part as well, like that. Okay, so we want to avoid kind of repeating ourselves, or specifically just having the exact same memory multiple times. That's very wasteful. Now, obviously for a square or for a rectangle, it might not seem wasteful because there's not much to it. I mean, yes, we do have 50% more data in our vertex buffer because we're storing 2 extra vertices instead of storing 4, we're storing 6. However, when you think about a 3D model, right? Maybe you've got a character in your game or a spaceship or whatever it may be, right? Every single triangle that makes up that ship or that character is going to be connected to another triangle, right? Which means that you're immediately already repeating at least 2 vertices. And then maybe there's another triangle up there, right? So you can kind of see how this just kind of escalates out of control, and you might have so many extra vertices. Not only that, but when you're actually rendering 3D graphics, and potentially in like, maybe you're using something like physically based rendering, your vertices might be pretty big. You might have vertex positions, normals, texture coordinates, binormals, tangents, colors. That might all be in one vertex. And if you have to duplicate that entire kind of buffer that makes up that actual vertex again and again and again, that's just going to be completely unrealistic, right? Just having a simple index instead is going to be much quicker and much more efficient. So let's just convert this kind of.
So wait, hold on.
You can kind of species, and then maybe there's another triangle up there, right? So you can kind of see how this just kind of escalates out of control, and you might have so many extra vertices. Not only that, but when you're actually rendering 3D graphics, and potentially in like, maybe you're using something like physically based rendering, your vertices might be pretty big. You might have vertex positions, normals, texture coordinates, binormals, tangents, colors. That might all be in one vertex. And if you have to duplicate that entire kind of buffer that makes up that actual vertex again and again and again, that's just going to be completely unrealistic, right? Just having a simple index instead is going to be much quicker and much more efficient. So let's just convert this kind of vertex buffer that we have now. Let's add an index buffer to it and remove that duplicate redundant memory. So if I go back to my source code over here, what I'm going to do is make an index buffer. So the way that we do this in kind of, well,
You should generate a new buffer, right?
Really. If we get rid of all of the redundant stuff inside this array, right, so that we only have unique vertex positions here, what I'll do is I'll get rid of this one because it's a duplicate, and I'll get rid of that last one because it's a duplicate, right? So now what we have is basically this. And if I go back to Illustrator just so you guys can visualize this a little bit easier, I'm going to make this color green or something like that, right? This is our index 0, this is index 1, this is index 2, and this is index 3, okay? So 0, 1, 2, 3. Each line over here, I've kind of divided it line by line, is a single vertex. And of course, if we kind of number these vertices starting from 0, we get a sort of index. So if I was to create...
So let's get rid of the redundant data. So this part is redundant, right? So we get rid of this, then we have another one which is this part right here, and then we get this, right? Should be the same. Yeah.
An unsigned int array here called indices, and I just wanted to basically draw that same square that I had before. What I could say is use the first vertex, the second and the third vertex to kind of get this first triangle over here like that. So that would be 0, 1, and 2. If we kind of refer to our vertices like this as if they were indexed.
No, I use open source stuff. No thanks.
Kind of get this order, right?
So we have this is the first, so this is first, this is the second, this is the third, and this is the fourth, right?
So 0, 1, 2, and then for the second...
So 0, 1, 2, and then probably 2, 3, 0. I'm still streaming, yeah. Let me check if I'm still streaming because, yeah, okay.
In triangle, I want to do 2, 3, and 0, right? Because that's this
Yep.
position, 2, right? 3, and 0, which is how we can kind of draw this triangle, the second one. So 2, 3, and 0. And that is actually an index buffer. We've just created exactly the data we need to tell OpenGL how to render this triangle, or rather this square, without providing it with redundant or duplicate vertex positions and all of that, or vertices, I should just say, because obviously in this case we've just got positions, but there could be a lot more data in there. So now all that remains is actually, instead of having this data here, these indices here on the CPU, we want to actually send them to the GPU and then tell OpenGL to render.
Should generate a buffer,
okay?
right?
And the way that we do that is very, very similar to the way that we actually make
Yeah.
a vertex buffer. So let's copy this. I'm going to put this after our kind of vertex.
Yeah, we should generate and bind the buffers. So let's do this real quickly. Where does this happen? Okay. Before we build around the shaders.
Attribute stuff, just paste it here. I'm going to rename this IBO, which stands for index buffer object, because it's kind of like our ID or our object which represents this particular index buffer. We're going to generate a buffer the exact same way that we generate a normal buffer. The only real difference here is that instead of binding this as an array buffer, which represents this particular index buffer, we're going to generate a buffer the exact same way that we generate a normal buffer. The only real difference here is that instead of binding this as an array buffer, or specifically to that slot, to that GL array buffer slot, we're binding it to a GL element array buffer. Okay, so I'll just make sure that I'm doing that for both the bind buffer and buffer data. The buffer that we're binding is of course this
wait. Let me just add array buffer. Oh fuck, array buffer. Does this exist? Yep. Okay. And the same thing we do here. Now we have to specify the. Okay, this is size of int, and we have 6 times 3 elements, and I'm not sure what I should put here. No, so that's IBO, and indices is the
IBO that we've just generated. And finally, when we supply it with data, instead of supplying it with positions, we supply it with these indices. So I'll just write indices. And then of course the size of them is in this case going to be 6 unsigned ints. Now keep in mind that I've...
Oh yeah, that's unsigned int, okay. It's kind of the same thing, but I'm gonna just
chosen to use unsigned ints here because we'll probably likely be using unsigned ints in the future. However, you can just use unsigned char or unsigned short if you want to kind of save memory. Char of course being 1 byte, short being 2 bytes. Integers are 4 bytes, so they are a lot more memory than say a char. However, obviously you have the restrictions of if you use a char, you only an unsigned char, you only have 0 to 255, so you can only have 256 different indices. We're going to use unsigned ints for all these examples because there's not going to be any measurable performance difference in this case, and in the future when we have pretty complex models we'll likely want to be using unsigned ints anyway. The key here is that it has to be unsigned. You cannot use a signed type, okay? It has to be unsigned. More on that later. So down here, I'll just verify that we do have 6 times unsigned ints, which is exactly what we've got in our actual array, and then we're of course taking it in over here. So looks pretty good, right? So what else do we need to change? Well, the last thing we need to change is our actual draw call. Instead of being GL draw arrays, it becomes GL draw elements. And the mode here is the same. We're drawing triangles. The count is going to be 6 because we're drawing 6 indices. This is the number of indices we're drawing, not the number of vertices we're drawing. The
Okay.
type is the type of data that is in the index buffer, which in this
Wait.
again over here, draw call. Instead of being GL, so what else do we need to change? Well, the last thing we need to change is our actual draw call. Instead of being GL draw arrays, it becomes GL draw elements. And the mode here is the same, we're drawing triangles. The count is going to be 6 because we're drawing 6 indices. This is the number of indices we're drawing, not the number of vertices we're drawing. The type is the type of data that is in the index buffer, which in this case is GL unsigned int. And finally, this is a pointer to that index buffer. Now, because we've got a bound in this actual slot here, we've actually, you can see GL bind buffer, element array buffer. This element array buffer is a slot for index buffers, and we've bound our IBO to there. We don't actually have to put anything here, so I can just write null pointer. And that's it. That's all.
Okay, so we have to replace this. I'm just gonna comment this out, and then we draw elements, right? And then this is always GL triangles. We have to specify GL unsigned int, right? And then we should pass null pointer like that, right?
All we've got, this is the actual draw call that draws our triangle using 6 kind of vertices, right? But you can see obviously our vertex buffer only actually has 4 vertices, and then we've indexed into that. So let's hit F5 to run this program, and you can see we get a beautiful rectangle. Now that's great. I did mention something about these having to be unsigned, and this is actually going to lead in great into the next OpenGL episode, but let's just deliberately make some kind of mistake that's pretty easy to accidentally make. Let's just say that instead of writing GL unsigned int for some reason here, I wrote GL int, okay? Looks pretty harmless. I mean, yeah, int, unsigned int, is there really that much of a difference? I mean, obviously there is, but let's just say that we didn't know that. Let's hit F5, and look at that. We get a black screen. We get absolutely nothing printing in the console except for that OpenGL version. What's going on here? Well, what you've done is you've used an invalid enum. You've used int, whereas this buffer, or any index buffer, has to be made up of unsigned integers. Not signed integers, unsigned integers. So of course in our case, we know what the problem is, we can just bring this back. But you can imagine how some people, when they write this code, might make the mistake. I've made it before, hundreds of times probably, and I've wondered, why do I have a black screen? This is going to lead us into our next episode, which is going to be about OpenGL errors, and specifically what we can do to deal with errors in OpenGL. Because you can see if I just give it an invalid enum, like I just did right then, it's not going to say anything to us. We have no idea what we've done wrong. Instead, we get a black screen and nothing's working. That can be an absolute nightmare to diagnose and debug, especially if you're new to OpenGL. So next time, we're going to talk about errors and what we can do about them, how we can best kind of get error reporting back from OpenGL, and like basically just make the best of errors in OpenGL so that we can know immediately when something goes wrong and specifically what goes wrong. That's going to be making light of a bad situation because OpenGL, just telling you right now, OpenGL debugging is very, very bad. Anyway, just to recap index buffers, what we've actually done is we've removed any kind of duplicate vertices that we may have here. We've just got absolutely completely unique vertices in this vertex buffer now. What we've done is we've created an index into that vertex buffer to allow us to kind of draw vertices more than once. And then we've actually sent that index buffer to the GPU using this code here. We've created one, and then we've actually sent this data to the GPU using this line here. And then finally, we're using GL draw elements to draw using an actual element buffer or an index buffer, as they're more commonly called, instead of GL draw arrays, which is just going to kind of draw our vertices sequentially. And that's it. That's how we can draw a square in OpenGL using an index buffer. And that basically what you see there, this setup, vertex buffer, index buffer, and GL draw elements call, that is probably how we render 90% of our stuff onto our screen in OpenGL, even in a full-on professional like AAA game. That's how you do it. GL draw elements is the function to be using most of the time. Anyway, I hope you guys enjoyed this video. If you did, you can hit that like button. If you want to help support this series and...
That's cool, that's cool. So we usually use this, right? We usually draw elements because we have to store the indices, like for each triangle. And indices is like pointing to an existing information to avoid redundancy, and yeah, this is pretty much how it works. Okay, that's what we did so far. Like we created a simple function to import, to import the shader data, and then we did this. Like we created a new buffer. This buffer is stored in, of course, inside the VRAM, inside or GPU. Then we binded it, and then we are using it. And that's pretty much it. Okay, I'm gonna take a short break, so I'm gonna be right back as soon as like in a few minutes. Okay, so okay, so see you in a few minutes. Did I mute myself? No, I mute myself. Okay, guys, we are back here. So let's keep going. Let's keep developing. Let's keep learning OpenGL. So right now we are using indices to point to vertices, to already existing vertices, and for now we enable the position attribute for the vertices. So we are reusing this attributes, right? So let's keep going.
Make sure the new episodes come out as often as possible as
Oh
well.
yeah, this video is, and so let's go here. I don't care, Amazon, don't do this. And
Chan, and welcome back to my OpenGL series. So today we're going to be talking all about errors. Last time we were able to use index buffers, and I even mentioned one thing that you might do wrong that would cause an error to appear and actually just not display anything on the screen. Check out that episode if you have.
wait, what was the one thing that caused the error? Wait, what is the one thing that caused the error? Oh right, it's the unsigned int. Yeah, but that is really annoying. Yeah.
Haven't already, but today we're going to figure out what we can do to actually be notified, or how we can find out what has gone wrong with OpenGL when we do something incorrectly. That's a very big part of OpenGL, because OpenGL, like a lot of things, tends to be fairly fragile and we can upset it pretty easily. That's okay, that's just a normal part of development. How do we know what we've done wrong, and how can we debug this as quickly as possible and fix it so that we don't have to spend the whole day wondering why our screen is black? Okay, so there's a few ways to deal with this. We're not going to talk about using external tools or anything like that. We're just going to talk today about what OpenGL actually gives us as a way of checking for errors and all of that. So basically, right now, we have two main ways that we can check for errors in OpenGL. One of them is called glgetError. It's a function we can call. It's been in OpenGL since the very beginning, and so because of that, it's compatible with all versions, and it works in a very simple way. Basically, whenever we call an OpenGL function, if an error were to occur, a flag kind of gets set internally in OpenGL's memory that basically says what type of error occurred, and when we call glgetError, that gives us back a flag, right? And by flag, I just mean like an integer, basically. That's like an error code. And if we actually keep calling glgetError, it will kind of give us all the flags, because sometimes it's possible for us to generate multiple errors if you're really bad at programming. If you've done something really bad, you might even have caused several different types of errors with a single OpenGL function call. And so because of that, glgetError will actually set like maybe 3 flags of 3 different types of errors that have occurred. And when you call glgetError, it gives you one of the flags, just an arbitrary flag. So you kind of have to keep calling it to get all of them. But basically, that's just us kind of polling OpenGL, us asking OpenGL, hey, is everything okay? Have I caused any errors? Now that strategy is okay. The way that it's typically set up is that since pretty much any OpenGL function that we call might cause an error, let's actually take a look quickly at what an error might look like in OpenGL to begin with. So right now, since the last episode, we have this beautiful blue square rendering. Now what I'm going to do is just close this, and inside my glDrawElements call, which is my actual draw call, I'm going to change this unsigned int enum, which specifies the type of index data that we actually have, to just say glint. This is one of my favorite errors to demonstrate, because it's really simple. I've made this mistake plenty of times, and it's fairly effective. Let's hit F5. You can see that all we get is, well, a black screen. Our square, our rectangle, is just not rendering at all, and you can see that in the console, of course, nothing gets printed at all except for our OpenGL version that we're printing. We just get a black screen, and this absolutely sucks. I mean, I hate this. Getting a black screen and then having to figure out what you've actually done wrong in which line. Like maybe you haven't set up your vertex data correctly. Maybe your index buffer's not correct, right? Maybe your shader doesn't work. Like, what has gone wrong? It's very hard to tell, and in this case, of course, we're just sending glint instead of glunsigned int as the index buffer data type. So it would be great if we could just get OpenGL to tell us, hey man, your GL draw elements function, you're passing an incorrect enum in there. You should fix that, right? That would be fantastic. So the typical kind of workflow that we have with GL get error is, first of all, pretty much before every function call that we give to OpenGL, we clear all the errors. So we basically just call GL get error in like a while loop until it equals no error, which means that we've kind of retrieved every possible error from OpenGL. That's just a way for us to actually clear all of the pending kind of errors. Then we call GL draw elements, and then we call GL get error again. And that way we can kind of see, has this previous function called GL draw elements, has that generated any kind of errors? And if so, which ones? And then we can kind of print that to the console or something like that to figure out what went wrong. So that's one way of dealing with errors in OpenGL. It's pretty much the most common way, the most popular way, because it has been in the specifications since 1.1, since the very beginning, and it's compatible obviously with pretty much everything. Now recently in OpenGL 4.3, so it is quite recent, OpenGL added a function that basically lets us, well, it's called GL debug message callback. If we take a look at the documentation real quick, it's called GL debug message callback. You can see that it's been added in OpenGL 4.3. And basically what it is it allows us to specify a function pointer to OpenGL, and OpenGL will actually call that function of ours when an error occurs. Now this is much better than GL get error, because first of all, instead of us having to constantly ask OpenGL, hey, are you alright, man? Is everything okay? It will tell us itself when something goes wrong. The only thing with this is obviously the fact that it's in OpenGL 4.3 and above, so you can't use that in earlier versions, but also another really good thing about this is it will actually give you more detailed information. Instead of just giving you an error code, which is kind of useless, like completely useless, it will even suggest things like, it'll explain to you what you've done wrong in English. Like, it's amazing. It's kind of dependent, of course, on drivers and stuff like that, but in my experience, it generally has been very, very good and much better than GL get error. Today, we're just going to be focusing on GL get error completely. It's going to be just totally about GL get error. That way is still good, and it's obviously compatible with every version of OpenGL. But then in a future episode, I want to devote like a whole episode to...
Oh my god.
...back and talk... And in a future episode, I want to devote like a whole episode to GL debug message callback and talk about how we can actually use that, because it is much better, but obviously it's not really compatible with every version of OpenGL. Alright, anyway, let's talk more about GL get error. So if I flip over to the documentation here for GL get error, apart from telling us, of course, what it does and the fact that GL no error is what it returns when we don't have an error, which you can see also that GL no error is guaranteed to be 0, so that's useful information here. It also tells us that calling it will return an arbitrary error flag, so not necessarily all of the errors. And because of that, we should call this in a loop to make sure that all of the errors are reset and we kind of get information about all of the errors that have actually occurred with OpenGL. So that's kind of like important information that you definitely need to pay attention to. We should be calling this inside a loop to make sure that we get all of the errors. Because if you don't kind of do that, then maybe you might be clearing an error just by calling GL get error, then you call a function and then you get 2 errors back. And you actually didn't realize that, oh, actually one of them was from another function I called early on because I didn't clear all of the errors. So just make sure you kind of read this, because the worst thing about GL get error is if you can't even do that properly and then you don't even know what's happening. Alright, so let's flip back to our code and let's actually add all of this. So what I'm going to do at the very top is make a function, and I'm actually going to do this at the very top. I'm going to make a function, static void GL clear error, and I'm kind of just writing GL in capitals here at the beginning of this function, just to kind of let ourselves know that it is kind of an OpenGL internal kind of function that we're writing here. And the purpose of this function, of course, is just to clear all the errors, so all we really need to do...
So let's try this. Let's create a... Right on the top, we will create static void GL error. Oh, I mean GL clear error. Something like this. And then it's a while loop, of course. And after this, probably there is something like GL error, GL get error, probably. It's probably like that, and it gets assigned to somewhere, like probably on unsigned int error, something like that. I'm just trying to, I don't know, I'm trying to get the error. I'm trying to think something, attempt to guess.
Is called GL get error, just like that. And while that doesn't equal 0, so either the way you could kind of write this is does not equal GL no error. So while we actually have an error back from OpenGL, let's kind of keep looping through this. So I'm just gonna add a semicolon here, and that's it. We don't really need a body. We don't care about error codes at this point in time. We just want to clear all the errors, that's all.
Okay.
Now, another way you could write this, obviously, because GL no error is guaranteed to be 0, as we read earlier, you could just kind of write this like that. So while GL get error is not 0, then keep kind of looping, keep retrieving all the errors. But I am trying to keep this code a little bit more clear for people who are learning OpenGL, so I'm just going to write it like this. Okay, cool, so we now have a way of clearing errors. Let's write another function here which will actually print an error that does occur, or all of the errors that do occur after a function call. So I'm just going to make this a void function called GL check error or something like that. And all this is going to do is basically, well, kind of the same thing as the other function is going to GL get error. However, instead of just kind of ignoring this, we're actually going to assign it to something. So GL get error, as you know, returns a GL enum, which is just an unsigned int, but because this is such a closely kind of tied GL call, I will actually use GL enum here. So while GL enum error equals GL get error, so I'm assigning it here. Okay, so I'm kind of retrieving the error and assigning it to error, kind of all in one line. Obviously, since this is inside a while
Yo, I'm back. Sorry, I had to interrupt for a little bit.
block, this while loop.
So that's what I did here. So yeah, we can just do this. We can just get rid of this, and
Loop will run as long as GL get error, as long as this kind of error variable is not 0, so it's not false. So while we kind of have errors that we are actually retrieving, let's go ahead and just kind of print them out to the console. So I'm just going to write standard cout, kind of format this nicely, so maybe OpenGL error, and then in brackets, I guess, we'll actually put that error code. And that's it for now.
Okay, so let's just print it. So yeah, we have this. This is an integer, but I will print it anyway. So std count. Then we have this OpenGL error, and then we will print print this error. Then we will add this, and then we will add std and okay.
Alright, pretty cool. So now we have a very, very simple way of actually checking to see if we have an error. So let's just test this out. So I'm going to go down here to my draw function. Now I have made a mistake here, right? You can see I'm using glint and not unsigned in. I've still got that code in. The first thing I'm going to do is call gl clear error, right, to clear all of our errors. And then finally, gl check error after the function. So you can kind of see how this works. We clear all the errors first to make sure that we don't have any other errors from other functions. We then call our actual function, and then we check errors. That way we can kind of make sure that all of the errors are actually coming from this function, and we're just getting the errors from our last function call. Alright.
Okay, let's try this. So we have, let's add this, let's add gl check error, not here, wait, oh god. GL clear error, then we have this, just like that, right?
So now let's just hit F5 and see what happens. Okay, look at this, check this out. So in our rendering loop, we're actually getting, if I just pause this for a sec, we're actually getting OpenGL error printing and then 1280. Fantastic, so we know that we've done something wrong. And if we go back to our documentation, you can see the following errors that we actually have defined. Now, which one of these is 1280 is the real question. To figure that out, let's go ahead and actually go to our OpenGL header file. So this will be in glue for us.
And this should be an hexadecimal value, right?
If we type in 1280, we're not actually going to get anything because OpenGL defines all of its enums in hexadecimal notation. So what we'll actually have to do is convert that error code from decimal into hex. To do that, I'm just going to stick a breakpoint into this error function here. I'm going to unselect this so that it resumes my program. You can see we have 1280. If I just right click here, I can go hexadecimal display, and you can see the error code is just 500 here in hex. So if I go back to my glue header file and search for 500, maybe a 0x0 at the beginning, you can see that here we have all of our invalid kind of errors, right? All of our error codes. So 500 means invalid enum. Now, at this point, it would be very wise for us to actually write a function which translates all of our invalid kind of errors, right? All of our error codes. So 500 means invalid enum. Now, at this point, it would be very wise for us to actually write a function which translates these numbers into actual words. So basically, if our error code is gl invalid enum, as it is here, maybe print invalid enum to the actual screen. That would be nice, but I'm not going to do that here just not to waste time. So you can see that our error code here is invalid enum, which tells us that we've actually passed in an invalid value into an OpenGL function, and specifically an invalid enum. Now in this case, that of course makes sense because glint is the actual invalid enum we've passed. It should be unsigned int. You can see though that there are a few flaws with what we've done here, and it's not that it's flawed. It's just that it's not that great, right? I mean, we know we're getting an error. We know it. We can kind of deduce that it is inside the render loop, and it's not in all the kind of OpenGL initialization code or anything like that we did, such as creating our vertex or index buffer, because we're getting errors like every frame basically. So we know there's something here, right? What we don't know is actually which line of code it occurred on. So that's kind of an issue. And not only that, but you can see the code is a little bit clunky. I mean, if we have to go back to every frame basically, so we know it's something, we know it, we can kind of deduce that it is inside the render loop and it's into actual words. So basically, if our error code is gl invalid enum, as it is here, maybe print invalid enum to the actual screen. That would be nice, but I'm not going to do that here just not to waste time. So you can see that our error code here is invalid enum, which tells us that we've actually passed in an invalid value into an OpenGL function, and specifically an invalid enum. Now in this case, that of course makes sense because glint is the actual invalid enum we've passed. It should be unsigned int. You can see though that there are a few flaws with what we've done here, and it's not that it's flawed. It's just that it's not that great, right? I mean, we know we're getting an error. We know it. We can kind of deduce that it is inside the render loop, and it's not in all the kind of OpenGL initialization code or anything like that we did, such as creating our vertex or index buffer, because we're getting errors like every frame basically. So we know there's something here, right? What we don't know is actually which line of code it occurred on. So that's kind of an issue. And not only that, but you can see the code is a little bit clunky. I mean, if we have to go back up here and basically call clear error and check error before every function, like clear error and then check error, that's going to just pollute our code and make it so much hard to go back up here and basically call clear error and check error before every function, like clear error and then check error, that's going to just pollute our code and make it so much harder to read. Like, why would we want any of that? That's going to just...
I will use a macro. I will use a C++ macro instead, right?
burden us with error checking, which we should be doing just automatically all the time, right? So there are a few ways of dealing with this. For our first problem, it'd be nice for us to know the line of code on which this error actually occurred on. Now, we can kind of do that manually ourselves. If we kind of resume our program here, so it is running, it is still kind of spamming all this to the console. I did place a breakpoint here in this GL check error function to figure out what kind of value this was in hex. You can see if I look at the call stack and I double click over here, I know that it's happened on this line, which is GL draw elements. So I do kind of know what line of code it happened on. However, that involves me placing a breakpoint and all of that. It's not too fun. And also, in this case, we kind of know what line it happened on anyway, because we're only checking one function for errors. But what we can actually do is get our actual debugger to just pause execution and break on the line that causes that error, right? And we can do that by just using an assert, basically. An assertion is when you assert if something is true or false, and if that kind of condition is false, you typically like either write a message to the console or just kind of stop execution of the program and kind of break on that line. So it's kind of like placing a breakpoint, but we can actually place a breakpoint through code, right? We can actually tell our kind of debugger, hey, if you run into this line of code here, into this function that I'm calling, break. Instead of breakpoint here and just break, right? It's pretty cool. We're definitely going to talk more about assertions in the C++ series. I'll have a link up there once that video is made. But let's take a look at how we can actually do that. So to do that, I'm just going to kind of rewrite this check error function a little bit. I'm going to first of all get it to return a boolean. Let's just stop execution of our program as well. And I'll call this GL log call, okay? Because we'll add some more features to it in a minute. Now,
okay, let's do that. So we have, this is a bool, and then we have GL log call. Okay.
If this does return an error, and in fact, as soon as it does, I'm just going to call return false here. Now, you might kind of question the validity of this loop now. Why does this have to be in a while loop if you're returning from the first iteration? But this is just kind of to demonstrate for now, so I don't really care. And then return true. So basically, if we return false from this, it means that our GL call was not successful. I'm then going to come up here, and I'm actually going to write a macro, which is our assertion, right? So define assert X. So all this is going to do is validate a condition. So we'll have to write it like this. If you kind of write it like this, it won't really work because of reasons. We'll have a video about C++ like this.
Okay, so we write our assert macro like this, then
kind of write it like this, it won't really work because of reasons. We'll have a video about C++ macros and all that. Again, I'll link that up there when that's actually made. But we have to write our condition wrapped in parentheses like this. And if this was false, I'm just going to call a function which will basically insert a breakpoint at that moment in code and just break the debugger. So this is an intrinsic to your compiler, which basically means that this function that you call here is going to be different for each compiler that you're using. When I cover assertions in the C++ series, I will show what the function is for like all compilers. and all of that. I'm sure you can Google it anyway. But because we're using Visual Studio here, and this isn't really about C++, it's about OpenGL, I'm just going to use the MSBC function, which is __ debug break, like that. The _ kind of lets us know that it's a compiler intrinsic, which means that it's specific to MSBC and it won't work in Clang or GCC or any of those compilers. Okay, so that's pretty cool. That's our assertion function. So what I can do now is basically where we have this GL log call over here at the bottom.
Wait, did I just mute myself? No, I didn't. Okay.
And this GL check error, well, actually it's called log call now. Let's just rename it to log call like that. I can assert that. So I'll write assert and I'll wrap this in parentheses like that. And I'll hit F5 to run my program. So if this returns false, it should just break the debugger. And you can see, look at that.
Okay, let's try this. So we have GL log call, and then we have to assert this, right? And then we have it, right? Everything is inside this macro, right?
That OpenGL.exe has triggered a breakpoint on this exact line. We know exactly now our program does not continue running and doesn't keep spamming the error into our console. Our console just reads OpenGL error 1280, and we can see where that error occurred. How cool is that? Much better, but we can do a lot better than this. The next step is...
Yeah, we can create an entire macro that honestly handles everything, even GL clear error.
Actually
right?
going to be just to get rid of having to call clear error and then log call after every function. Let's invent some kind of macro that does that for us. So if we go up to the top where we define all of our macros, I'm going to define another one called GL call, right? X is going to be the function essentially that we're calling. And over here, the first thing that I'm actually going to do is call GL clear error to make sure that we clear everything. Now, I don't want to write all of this code on one line because it'll be hard to read, so I'm just going to add a backslash and then hit enter. This basically ignores the new line character so that we can continue writing this macro on the line. Right. I'm then going to just write x, comma, which basically will insert that function we've specified so that we call it. And again, another backslash. Now, one more thing I have to mention is make sure when you put the backslash, you don't insert a space and then enter. Otherwise, you still got the new line character there. You have to put a backslash and then with no spaces, press enter. And then finally, I'm just going to call GL log call, but this time actually inside an assertion. So like this, GL log call, like that.
So let's try this so we can, define GL call I would probably use GL log, right? Then X, then I will call GL clear error like that. Then we do this. Nope, we do this, and then we call GL log call inside assert, right? Just like that.
And I'm not going to put like a semicolon or anything over here because we don't need to. Because after we call GL call, we'll end it with a semicolon. Alright, so now let's scroll down to our code here. And instead of having to call GL clear error and then asserting that log call, what we...
Yeah, we can directly do this. So we can GL log do this. Just like that, and then we can get rid of this. Honestly, I would just comment to keep track of what I did here. Oh god, what the hell? Yeah.
What we can actually do is just wrap this GL draw elements with a GL call, just like that. How cool is that? And now we can hit F5. Alright, and we get the same result here, but you can see now it's even more clear. It's actually on this GL draw elements line, so we know exactly what's gone wrong. Now, one more thing we can actually do is this error message doesn't specify which file or line the actual error occurred on. We don't really need that because we're running through the debugger and it just breakpoints, right? And it's easy for us to see what file and line. But if we're running it without the debugger or anything like that, it would still be nice for the console, right, to somehow print out the file and line of code that this actual error happened on, maybe even the function name. So let's see if we can do that.
Hold on. So we have this and this. Okay, I know what's going on.
Let's go back out of here, and what I'm actually going to do is make this GL log call accept some more parameters. So we'll add const char function, which will be the name of the function we tried to call, with all of its...
Yeah, that's what I wanted to make at first. Like, I wanted to create like a little string thing to recognize, like to name these errors, right? Then we have a const char, then we have the function
arguments and everything. We'll add const char file, which will be the C++ source file where this function was actually called from, and then finally int line. So what I'll do to this error is I'll add all of those details. So when we print our error message, I'll also add in the function, which will be just function. I'll actually move this down here so you guys can see. We'll add a space after that function, then we'll add file, then maybe a colon like that, and then the line of code.
Okay, yeah, we can do something like that. So let's do this. So we have function, then we have probably this will contain the file, and then we have semicolon, a semicolon right here, and then the line, right? That's what we have.
Okay, great. So now we need to fill all of that information in. So inside this GL log call, we can actually use macros to figure out which file and line we call this function from. And not only that, but we can also, since we are actually passing in this function, we can actually turn in whatever x is into a string, and that's how we'll print our function name. And so to do that, I'm just going to write hash in front of x, which turns it into a string. And then for the file, it's underscore.
Wait. Did I just forget to add the parentheses here? Okay. So we have x, then we have
underscore file in all caps. Now,
this is the file macro, and then
like the debug break, this is not an intrinsic. It should be supported by all compilers, so don't worry about that. And then finally, for the line again, it's just underscore underscore line like that. Okay.
Okay, so
pretty cool stuff. Let's try and run our code again. Now when this breaks, if we go back to our console, check this out. We see GL draw elements with our actual parameters, GL triangle 6, GL int, and null pointer, and then we actually have a full path to this application.cpp source file, followed by the actual line of code 166, which you can see is the line of code that breakpoint is on. How cool is that? So we now know exactly what's gone wrong, where, and what we've actually, what code we actually tried to call that failed, because we're printing it all to the console. Pretty cool stuff. Now I know this is a lot to take in if you're not familiar with C++ macros, which is why that video, when it's ready, will be linked up there and all of that, and I should do that probably very soon. But you can see with the power of C++ and macros, we can really improve this OpenGL debugging. And specifically, the most useful feature here, to be honest, is that actual debug break. Just being able to break on that actual line via that assertion that we've kind of created is really, really useful because it kind of lets us know exactly where we've gone wrong. Now, what you should do now with this GL call is actually pretty much every OpenGL function we ever call, so like GL gen, just everything, we should be wrapping that with GL call. So basically what I'm going to do here is just do that really quick.
That's why you call it like that. Because you're basically using this for each OpenGL function. That's probably why. Yeah, I agree with that. So we should wrap everything inside GL call. Yeah, this would be much easier to debug. Yeah, I agree. So let's do this. It's actually kind of annoying doing all of this, but anyways, let's do this here. Then we do this. Let me just oh my fucking god. What's the fucking yeah. So let's go. And let's do this. Oh my god. So we should
every single OpenGL function call surrounded in GL call. Now, because I wrote this macro in a very simple kind of way, there are a few flaws. For example, if we use a one-line if statement, this isn't going to work because just the first line is going to be inside the if statement and these two won't be and all of that. You can fix that by just surrounding this in a scope or in like a do while zero loop and all of that. Again, I'm going to talk about that in the macros video. So kind of take this function, this code that I've written here is just a really kind of basic, simple way of doing this. Also, putting it in a scope isn't very preferable because if you actually have values being assigned, like if you have the shader code that we wrote over here, you can see that calling GL create program actually assigns it. So we can still do that inside GL call, just make sure you do it like this. However, the issue is that if we were to wrap that in a scope, program would be out of scope over here. So if we were to kind of put curly brackets like that around this to keep it all in one scope, then we have the issue of not really being able to use program over here, because it's like if we wrapped program in its own scope, kind of like that, it wouldn't be accessible anymore, as you can see here.
That's what I was thinking about. Yeah, he's right.
So there are a few kind of setbacks that you have to be aware of and all of that. I'm going to go ahead and add GL call to the rest of all these functions. That source code is available for patrons. If you support the series by going to patreon.com/thecherno, you will receive basically the source code to every single episode, kind of episode by episode, and that will have all of this already written, of course. I'll do that. I'm not going to waste your time and just, write GL call on every single function in front of you because you kind of get the point. But anyway, that is basically OpenGL error checking, right? That's how I like to do it. I like to just wrap every single function call, every single OpenGL function call inside GL call, and basically that will just breakpoint whenever I have an error. GL debug message callback we will talk about in a later episode because that is also very useful and kind of theoretically means we don't have to do all of this, although I find I still like doing this because you do get the compatibility with earlier versions of OpenGL, and also there's nothing really wrong with this method. It's just that GL debug message callback does give you more information and is slightly more useful and all of that. Anyway, hope you guys enjoyed the video. If you did, you can hit that like button. As I mentioned earlier, you can support this series by going to patreon.com/thecherno and get some pretty cool rewards. Finally, we also have a Discord server where you can discuss this episode and all of that.
Okay, let's move on. We have uniforms. I have no idea what a uniform is.
Cherno, and welcome back to my OpenGL series. So, today we're going to be talking all about uniforms. What is a uniform in OpenGL or in graphics programming in general? What are they used for and how do they work in OpenGL? So first of all, uniforms are a pretty simple concept. They're basically just a way for us to actually get data from the kind of CPU side of things, so from C++.
So, okay, wait, hold on. How many? So this is the, okay. Yeah, I'm not feeling that productive lately, but
Plus, in this case, into our shader so that we can actually use it like a variable. So a really good example of that, we're just gonna jump into some code straight away today. A really good example of this is in our current application. If I just run that for you guys to refresh your memory, we have a blue kind of square or rectangle that we're actually drawing over here. If we take a look at the shader code, the way that we're actually getting that blue color is just by hard coding a color here, right? 0.2 red, 0.3 green, and 0.8 blue with a 1.0 alpha. Now, it would be great if we could somehow define this data in the CPU side of things, so in our actual C++, and possibly even update it as necessary. So the good news is we can do that, and there's two main ways of doing that. Today we're going to look at uniforms, but it's also possible, as you guys could probably tell from the vertex kind of video, it's also possible for us to actually get data from the CPU to the GPU via a vertex buffer. And if you guys haven't seen that video, definitely check that out over there. But today, we're going to be focusing on uniforms. I am actually planning to make a comparison video between attributes and uniforms, because those are kind of the two main ways of getting data kind of per object kind of that we're drawing from the CPU to the GPU. But today, again, explicitly about uniforms. So in terms of just comparing the two lightly, the big thing that you do have to know is that uniforms are set per draw. So basically, you can set a uniform up before you call GL draw elements or GL draw arrays or whatever you're using to actually do the drawing. Whereas attributes are actually set kind of per vertex. So in other words, you can see that obviously when you form the two lightly, the big thing that you do have to know is that uniforms are set per draw. So basically, you can set a uniform up before you call GL draw elements or GL draw arrays or whatever you're using to actually do the drawing. Whereas attributes are actually set kind of per vertex. So in other words, you can see that obviously the position attribute we have here, which theoretically could be any kind of data, in this case though it's a position, this is per vertex. Whereas with uniforms, we kind of set them before we do the actual drawing. So they're set per draw. That's a really big difference, and again, we'll explore that more in the dedicated video about that. So let's convert this color into being something that we set from C++. So the first thing I'm actually going to do is modify my shader. I'm going to go into my shader file here, and into this fragment shader, I'm going to add some code. So just underneath this output that we actually have here, I'm going to write uniform vec4 u_color. Now I like to use a bit of a naming convention here. I didn't really use it for attributes or anything, but as we get into uniforms, I'm going to start using it. Basically, anything that begins with a u underscore is an actual uniform variable. And in this particular case, it's actually necessary for me to differentiate this variable from, of course, the variable that is our actual output color. So that's all I have to do in my shader. That's it. I've declared a uniform. I can now use this uniform throughout my shader code, and in fact, what I'm going to do is replace this color with u_color like this. So we're basically assigning the output color of each fragment, of each pixel of our actual rectangle to be whatever this uniform value actually is. So now all that's left to do is to actually set that uniform from C++. So the two things that matter here are the type of the variable, which is a vec4 for a 4-component vector, we need to remember that, as well as the name, so u_color like that. Okay, let's go back to application and set this up. So what I'm going to do is, after my shader is actually bound, right? So I've actually called GL use program. You have to have a shader that's actually bound when you actually do this, so that it knows which shader to send data to. What I'm going to do here is called GL uniform, and then we have a variety of functions that you guys can actually check out in the documentation. Basically, the difference here is the type of data that we're actually sending and how many components we have. So how many floats are we sending, or how many integers are we sending? Now in this case, actually do this.
So we have GL use program. Oh, hold on. Let me just check if I actually put this everywhere. This is a little bit annoying, but should I do the same thing here? Probably. I'll just do this. Don't know if I'm doing it correctly, but yeah. Actually, this isn't a GL function. So then we have to do this. Then we have to do this. Oh god. And then I don't think I can do this here. Then we do this here. We do this here, and then we do this here, right? Then we do this here and here, then here and then here. It should be okay. Let's see if that actually works or not. Yeah, it works. Wow. So now what I need to do is create a uniform right here on this part. Can I comment like this? Yes, this is a comment. So we have to declare a uniform, and we call it uColor. Yeah. And then I have to, oh wait, this I also have to specify the type like this, and then I can get rid of this and set it to uColor, right? This is pretty much how it works for what I can understand. So where he defines the program, I mean right here, we should use GL call, and then yeah, probably use this.
Which shader to send data to. What I'm going to do here is called GL uniform, and then we have a variety of functions that you guys can actually check out in the documentation. Basically, the difference here is the type of data that we're actually sending and how many components we have. So how many floats are we sending, or how many integers are we sending? Now in this case we know it's a vec4, which is a 4 component kind of, which is basically just 4 floats. So we need to choose GL uniform for F, okay? So 4 because there's 4 of them, and F because they're floats. The first parameter here is the location of them, and F because they're floats. The first parameter here is the location of this variable, and you can see that it's actually an int. So what we need to do before we even call this is actually retrieve the location of this variable. So what OpenGL does is once our shader gets created, every uniform basically gets assigned an ID so that we can then reference it. And the way that we look up that ID typically is by its name. So we can basically ask our shader, hey, this u_color variable, please tell me what the location of that variable is, and then we'll get an integer back. In more modern versions of OpenGL, you can actually set an index, kind of the same way that we're actually setting this kind of layout location equals 0. So you can specify an explicit uniform location starting with OpenGL 4.3. So it is quite a modern kind of new feature, which is why I don't really like using it too much. And in this case, we're just going to retrieve it by using the name, because that's fine. So if we go back to application, what I'm going to do is just write int location equals GL get uniform location. And then we specify the program, which is our shader, as well as the name of the uniform we're trying to retrieve. So in this case, it's u_color.
That's cool. That's cool. Let's do that. So let's go here, and then we have int location, and then we have this should be inside of GI call. Let's do that. Then we have GI get uniform location, right, like that, and the program is buffer, and then we have to specify the identifier, right? So GI color, just like that. What the fuck? Oh wait, I have to do this. Yep.
Make sure that you obviously spell this and use the exact same casing as you do with the actual variable name in your shader here, because if you don't, then it's not going to work out. Now, we do have an assert macro, so I'm going to use it here and just assert that location does not equal -1. If we get the location -1, it means that it could not find our unit.
Okay, so assert location -1, just like that.
Uniform. Now that actually might be okay, because what you might not realize immediately is that that doesn't mean necessarily that you've made an error or that you've made a spelling mistake or something like that with your actual uniform name. If you don't use that uniform throughout your shader, so you have that uniform actually present in your shader but it's unused, then OpenGL will just strip that when it compiles the shader. So this might actually return -1 because the uniform's been removed, it's been unused. So you don't necessarily want to write out error or crash your program if it doesn't find your uniform, because you might have just rewritten the shader and maybe forgotten to remove it, or maybe you want it for later or whatever. So just keep that in mind. In this case, I'm just asserting it because I do actually plan on using it, and I want to make sure that I've actually done everything correctly. So now that we have a location, I'm going to feed that into here as the first parameter, and then you can see that we need to set 4 floats. So the first one I'm going to set is 0.2f, then 0.3f, basically the same code that I had before, 0.8f and 1.0f. So I've effectively moved my code from the shader into C++. And finally, I'm just going to wrap this int location call and this GL uniform call in my GL call macro to make sure we don't have any errors. Alright, so to summarize, I'm binding my shader by writing GL use program with that actual shader ID. I'm retrieving the location of this actual color variable. And then once I've retrieved that location, I'm calling GL uniform for f with that location integer, as well as the value, so that I actually set my data in my shader. And in the shader, all I've done is created a uniform by typing the keyword uniform, along with the type and the name, just like any other variable, and I'm using my uniform here to actually write to the output color.
That's
so
interesting.
If everything goes correctly,
That's cool.
I should be writing this color value into my actual output color for every single pixel in my rectangle. Let's run this program. And you can see we get the exact same result as before, so perfect, it's working. One other thing that we can do to check, just because obviously I am using the same color here, I'll just change the red channel to be 0.8, so we should get much more of a pink color here. And you can see, there it is. Perfect. Okay, so now let's do something a little bit more exciting. Let's actually animate this color and change it over time in our rendering loop. So back over here, I'm going to basically just set this uniform right before I draw my actual rectangle. So I'll copy and paste this code over here. I'll make a float called R, which will be our red channel. I'll set that equal to 0.0 to begin with. I'm going to feed in that R variable instead of 0.8 as the red channel, and then I'll just add a little bit of logic to animate it.
So hold on, let me just check if I see streaming. Okay, just in case. So we have RGB channel, so it should be 0.0 f. Yes, just like this, right?
So one thing I'm going to do here is set my increment to be 0.05f to begin with. If my R value is greater than 1.0f, I'm actually going to set my increment to be negative 0.05f. Otherwise, if R is less than 0, I'm going to set my increment to be positive 0.05.
So it will be like everything color, right? So this is like to assign like values in, it's something like this, right? So we use uniforms, right? Then we have to, to do this like this, and then we can just set this to RGB, then create like, I don't know, I followed this video. Like I can't think of an animation to do right now, but if this is 1.0f, then the increment will be minus this, or else the increment will be 0.05f. and then I have to probably do this.
5F, I'm not going to bother clamping R or anything like that because this is just a test really. And then finally R plus equals increment. So what this should do is basically just bounce between 1 and 0.
Right, never increment in function arguments. Never a good idea. Let's do this instead. Then we just put, you know, 0.3, 0.8, 0.3f, and then 0.8f, just like that. Fuck is wrong with you? What are you doing? Oh, right. That was done.
For the red channel. So let's run this. As you can see, what we get here is...
Yeah. It's like also if R just like that. Yeah, it works kind of. Yeah.
Between 1 and 0 for the red channel. So let's run this. As you can see, what we get here is a very party mode looking rectangle going very, very quickly because we're not actually limiting our frame rate. So let's have a go at doing that. What I'm going to do is scroll up over
Oh, we can limit our frame rate, right?
here to where we actually create our window. And what I'm going to do once we have an OpenGL context is just set the GLFW swap interval to 1, which should just synchronize this with our vsync, or otherwise our monitor's refresh rate, which for me is 60. So let's hit F5, synchronize this with our...
So let's go here, where we created the context, right? Where is this? Where is this? So we created the context here, yep, right here. Then we can get the GLFW and set interval, probably. Wait, what's the actual swap interval? Okay, and set it to 1. Then
our vsync, or otherwise our monitor's refresh rate, which for me is 60. So let's hit F5, and you can see we get a much smoother animation here. And that's pretty much it. That's what uniforms are in OpenGL. That's how you use them. It's really, really simple. Of course, in this case, we're just using 4 floats as an example, but you can use really any data type or any kind of number of components that you need to. So floats, integers, matrices, all of that stuff. We'll definitely be getting into that a lot more in the future. Uniforms are a really vital part of graphics programming and of OpenGL and all that. So as we actually start to build more and more, we'll be using them all the time. The really big thing that you need to keep in mind though is that uniforms are actually per draw. So obviously we set uniform for F and then we draw our entire piece of geometry, which in this case is just a rectangle. So they are actual separate OpenGL calls, so of course we can't in any way define uniforms or change uniforms, I should say, in between kind of drawing this. So if I had, so in this case I'm obviously drawing 2 triangles. I can't draw one of them with one color and one with the other color if it's set up this way, because at this point in time they're actually being drawn together in one draw call, and uniforms are set per draw. If I actually wanted those 2 triangles that make up our
yeah, you have to do the switch thing, right?
square to actually be different colors, I would need to do that via a vertex attribute essentially, and we can definitely talk about that in the future.
Okay.
Anyway, I hope you guys enjoyed this video. If you did, you can hit that like button. You can also support this series and everything that I do here on this channel by going over to patreon.com/thechannel. You'll get access to all the source code for these OpenGL videos, as well as some other exciting rewards, which you can check out by going to the link. Discord is another really cool thing that I like to promote, because there's basically what Discord is a community of people with which you can talk about all this OpenGL stuff or any other programming stuff. So Discord, thechannel.com/Discord, I always get that URL wrong. Go to thechannel.com/Discord and join that server. It's a great time. You can discuss this episode and all of the stuff that is related to programming. Maybe you're working on a project and you need some help. That's a great place to get it. Next time, we're going to probably move on to some more exciting shader stuff. I really want to start kind of abstracting this stuff out, and because we'll have to eventually kind of move this code into classes, because we'll be reusing a lot of it when we actually get down to drawing models and all of that stuff. So that's probably what's going to be in the next episode. There were a few other things that I definitely need to mention though. So I will see you guys in the next video. Goodbye.
Okay. My headphones are crushing my head, and when I wear it for too long, like for over, 30 minutes, it starts to to hurt my hair, to to hurt my ears. So we reached 1/3 of the series, and yeah, I learned a lot. Actually, I learned a lot. And in a few episodes, things will get interesting. Like you have textures, basic renders, now you have blending, maths, projection, and model view projection, matrices, whatever that is. Yeah, we have things like that, but I've learned a lot. So this is just day one. Like I started learning yesterday. Like it was night time for me. So this is day one of learning OpenGL, and as you can see, we know pretty much how things work, right? So if we scroll this code, like we know what each line of the code does. So like get shader IV, that's compile status, that we get the compile status of the shader. Then we get the log, and it will be stored here of the shader that has this ID, right? This is pretty much how it works. We have everything here. I wanna test the error. Like let's try to print that and then error this. Yeah, it errors out. Yeah. CPP dot 216, and it's right there. Yeah. Then we can mess with some things. So let's put one here. Let's see what happens. Oh, this is what's okay. This is a const point. Okay, so we have to pass a const void I don't know. I don't know what that is. Probably we have to reference um, the actual buffer, like indices. Let's try to do this. So this is what we need to probably. It's just a black screen and we don't even get any error from here. Wow. Probably I referenced the wrong thing. Let's try to pass the shader as a pointer. I don't know. It still errors. So let's pass. I didn't even read the argument name. So like, what is this function? What is this? Indices. Oh, I passed the indices, but for some reason it didn't read that properly. So I passed this. Why it doesn't work? It doesn't work. I passed the indices, right? And it should work. Or probably I need to pass this. Let's try to pass this. IBO. And I probably should cast this I const void. I don't know. Let's try this. Oh my god, it's literally this. Okay. It's literally this casted to const point to const void. It's the ID. It's literally the ID of the buffer casted to const void. So this pretty much does the same thing. That's cool. That will be useful. So this actually works. Like we can do the same thing, right? Wow. Yeah, this is pretty much how it works, like, right? So I will end the stream soon, but I will come back later because we have to learn more OpenGL stuff. Also, I wanna try to do something here. Like, I wanna try to learn this language. Like, I know that we are like there is this layout location equals to 0, and probably this is in out. I don't even know what that actually means, but I think I will find that out soon. And probably I will create a little engine That would be interesting, right? So how long am I streaming? Let me check. Almost 3 hours. Okay. We still have 12 minutes. So we have so many things, and the cool thing is that I'm slowly getting used to all of this. Also, we have an error. What kind of error do we have right now? What error do we have? Where is it? Oh, it was just an IntelliSense glitch. Okay. There is no error actually. If we build and run, yeah, here it is. That's cool. That's cool. We can do some pretty interesting stuff. We still have to watch 20 videos, but that's good. So let's see. Let's try to, explore this GL, this like this documentation, right? There are many things. There are many functions right here. Can we actually count those functions? Also, do we have like an interpreter for, to test or GLSL app? Let's try to check that out. Also, let me see if I'm still streaming. Yes, I am. So let's try to search for, GLSL tutorial. Like, do we actually have? Yeah. Stupid fucking ad.
Have you ever looked at a
Let
breathtaking
me
digital
just try
art piece
to-
and deeply wondered how they created that? There are many different approaches to digital art, but shaders might be one of the most powerful and versatile when it comes to creative coding. Shaders are like the paintbrushes of the digital
That's
age.
cool.
They allow you to turn a blank screen into a stunning animation in real time, and they're responsible for the stunning visuals in some of your favorite video games and movies. They can be used by creative developers in order to make 2D and 3D renderings exclusively using code, their
Yeah.
imagination being the only limit. Shader art coding is all about using mathematical functions and algorithms to manipulate pixels and create incredible visual effects. It's a unique fusion of art and science, where creativity and precision collide to produce something truly mesmerizing. But what are shaders, you may ask? In essence, shaders are small programs that run on your graphics card and are responsible for calculating the color of each pixel on a canvas. Shaders work by taking inputs, such as the position of the current pixel, and using them to calculate a single final color using the OpenGL shading language, or GLSL in short. It can be seen as a mathematical function that maps a 2D coordinate, the pixel's position represented as X and Y, to an output color which in computer graphics is represented by a red, green, and blue channel. This function is computed in parallel for every pixel on the screen, which means that shaders can perform millions of calculations per second to produce stunning real-time graphics. Since discovering shaders about a year ago, I've also made some of my own. It's really fun to learn a new computer graphics technique and make a shader about it. There are so many topics to learn from and so much space for discovery and original creation that it's impossible to get bored. While they're great at rendering stunning 3D scenes and even 4D for the particularly brave developers, shaders also excel at rendering 2D images and animations. They usually run blazing fast compared to some heavy 3D shaders that require more performant GPUs and compute power. For over a year now, I've been sharing my own trippy animations online, mostly in 2D, in order for shader coding to get known by a larger audience. Doing so, I've received many requests for tutorials and explanations about how to create such visuals using code. In this video, I will walk you through the creation of this shader animation from scratch to give you some insights about how to start making digital art using shaders. Additionally, I will provide some useful references and tools that can assist you on your artistic journey and that will be listed in the description. I assume a basic knowledge of programming, but don't worry if you don't know anything about code. I'll explain every step of the process, including the mathematical aspects, using visuals that, by the way, are also made with code. If you want to follow along with this video, you can head over to shadertoy.com. It's a platform where you can easily start writing your own shaders and share them with others, and it's a mine of inspiration and knowledge about computer graphics and digital art. I will start from the most basic shader that gets automatically generated when you click on New. Actually, I'll remove all of this.
Wait, what tool are you using? Hold on.
If you want to follow along with this video, you can head over to shadertoy.com. It's a platform where you can easily start writing your own shaders and share them with others. And
let's try that right now. Shadertoy.com. So we have everything here. So we can sign in. We have, okay, let me just, hold on, let me just wait. I'll do that later. I'll try to start using this right now. So we have a vector, then we have frag coordinates divided by the resolution, right? Then we have this, and then frag color, right? This is a weird, like, this is I know this is a real programming language, but you're not coding like functionality, or you're not coding tools or anything like that, but you are coding graphics, you are coding animation. This is a little bit this is interesting actually, and a little bit, weird because it's unusual for me, but that's really, really cool. And I will try to do this more because this really looks interesting. So what we have, like, let's try to set this to 1. What happens if we set this to 1? And I see that it's slowly faster. What if we put 0? Wait. What is S? Wait. What is this? Medium? Oh, okay, that's the font size. Okay. Wait. Wait, what? Wait, let me just go back here. I recompile it. So we have this. Now let's put 1. This is wrong operand types. No operation plus exists on the left. This is a const int, but okay, let's change this to 1.0, I guess. And everything works, right? Wow, this is cool. Wow, this is amazing. I really like the fact. We should try this more. Should we do this on a separate, on a separate playlist? Like, this is called trying to learn OpenGL. Should we also include this part, or should we or should we do it on a different series? Because this is really cool, and I'm really interested into this stuff. This is a vec 3, but actually this probably multiplies. This is probably a matrix multiplication that returns a vec 3, because this is a single number, or how's it called in math? This is a scalar value, right? This is cool. Let's keep watching that video.
It's a mine of inspiration and knowledge about computer graphics and digital art. I will start from the most basic shader that gets automatically generated when you click on New. Actually, I'll remove all of this to explain from the very beginning what is going on. Each shader is defined inside the main image function and has only 2 parameters. FragChord is the input parameter. It is of type vec2, meaning that it's a vector containing 2 values, the x and the y coordinate of the current pixel. FragColor is the output parameter, and it is of type vec4 because it holds the red, green, and blue channels, as well as an additional alpha channel which stands for the transparency of the pixel.
Yeah.
Let's assign a value to that output parameter. Here we set FragColor to a vector of 4 components using the vec4 keyword.
Wait.
Then specify.
What if we copy all of this? Like, I don't think this is gonna work, but let's try that out. So we copy this and we put this in the fragment shader, right? No, this isn't gonna work because we still have to define this. Probably it's color. Like, we should call this color, and it's a vec4, right? And then I don't know. I'm not sure if that actually works. Let's try to comment this out. No, we cannot. We need a frag coordinate and the resolution. I will do this later, right? So let's keep watching this video.
Specifying each component's value. The 4th value is the alpha channel. It has no effect in ShaderToy, so I'll keep it to 1. In GLSL, the output color is normalized, meaning that each channel ranges from 0 to 1. By setting all channels to 0, the output is full black. Remember that this code is ran for every pixel to determine its color. Here, the output color is a constant, so it will display a uniform black color across the screen. Similarly, by setting all 3 channels to 1, we can display full white. By playing with all the possible values for all 3 channels, we can produce millions of unique colors. I should also mention that there is a nice Chrome extension for ShaderToy that provides some useful features like this color picker that allow you to convert colors to vectors easily. It's called the ShaderToy unofficial plugin. Now, let's use the value of the input parameter in order to start seeing some better things than a uniform color. The range of FragChord is dependent on the size of the canvas. For instance, if you're rendering on a 1600 by 900 canvas, X will range between 0 and 1600, and Y will range between 0 and 900.
Yeah.
However, when working with shaders, we'll usually want to have these coordinates in clip space, ranging from -1 to 1, so that they do not depend on the current resolution of the canvas. So I will create a new vector called UV, which will contain our transformed pixel coordinates. The first step is to normalize fragcord so that its components range from 0 to 1. For that, we simply need to divide it by a vector containing the current canvas resolution.
Okay, yeah. Right, yes.
Fortunately, there's a global constant provided by ShaderToy called iResolution. It's a vector of 3 components holding the current canvas size in pixels. The first 2 components are the width and height of the output texture, and the third component is the depth and is only used when rendering to 3D textures. As we're rendering on a 2D canvas, we won't use the depth here, and the .xy syntax is used to isolate the width and height components of the resolution so that the division happens between vectors of the same size. I'd like to pause for a second here to discuss an important concept widely used in GLSL called swizzling. Writing iResolution.xy is equivalent to creating a new vec2 and assigning to it the x and y components of iResolution respectively. This concept can be extended further. For instance, if we wanted to create a new vector containing only the y and z components, but in reverse order, we could simply write iResolution.zy. These swizzling syntaxes are valid in GLSL and allow you to easily create, arrange, and
Wow, okay, that's cool.
reorder vectors into new ones. It's also important to note that when performing operations between vectors that have the same number of components, it acts as a shortcut, applying the same operation to every corresponding
So it's component for component, right? I think so.
component of the vectors. That when performing operations between vectors that have the same number of components, it acts as a shortcut, applying the same operation to every corresponding component of the vectors. So let's check if it worked. I will display the x value of this new vector in the red channel only, keeping green and blue to 0. We can observe a red gradient that aligns with the fact that the uv.x value linearly ranges from 0 to 1 as we move from the left to the right side.
So this is actually the frag color, like you get the. So if we go here, so let's change the frag color to be a vec4, right? And we will just display, this. What will happen? It's just blue. Or what if we add one here and then it's pink? That's cool. So wait, where is it? So then we have UV, and then let's multiply. So let's multiply this. We can also avoid this. We can just do UV, right? Dot X probably. And what if we do this? We actually get a gradient. That's cool. That's cool. We can do the same thing here. Let's put the Y, so the red should wait. This is this. Where is the origin? Is this the origin or this is the origin? Let's find out where the red spawns, right? And whoa, I already did something cool right here. Look at this. So this is the origin, right? The origin is at the bottom left corner. And look at it. I already like this. I already like this. This is so cool. And then we can store the green values inside the probably 1 minus u dot uv dot x probably, and that would be wait, hold on. This should be 1.0, right? Yeah. Wow. And then we should divide this. We should probably divide this. Not really. Probably we should multiply this by 1 minus this. Okay. I will keep it simple just to. But this is cool. Look at this. I really like what I did here. We can do the same. We can mix it with this and get a different result. And oh god, there is an unpleasant. I really love the right part, but I really hate the left part. But anyways, you can always change this, and it's so cool. I really like this. We can do a lot. We can actually do a lot with this, and then we can comment that out and get this part right here. Very cool. What is this? Wait, why do we have a volume here? We can also go for full screen. Guys, this is so cool. I really like it. I should definitely jump into this because this is really cool, right? So we are streaming for over 3 hours. I will end the stream for now. I look more deeply into this because Jesus. Thank you so much for watching, and I will see you the next time. Goodbye, everyone.